So let's take a look at inductively defined types. Now, what does that really mean? By types, we're talking kind of data structures. So things like integers, strings, lists, trees, hash tables. Those are the typical things that we work with in code. And inductively defined means that what the type is actually, each element of the type really is composed of some pieces that are just like it, right? So if you look at a tree, say a binary tree has a left branch and a right branch, each of which are binary trees, right? So that's an inductively defined type. Now, let's see if we can make that more precise. So really it's just a data type, right, that's defined using recursion. And here's the connection. I mean, recursion and induction are very, very intimately and deeply connected. And a lot of logicians actually use the word induction instead of recursion to talk about definition. So they'll say this is an inductive definition, where a computer scientist might say this is a recursive definition. Okay, so these are not mysterious, right? And here's an example. I mean, you may remember when we talked about formulas in propositional logic. So we said that T, or rather true and false, are valid formulas, right? And for anything else, right, then they're defined inductively like this. Suppose that we have alpha and beta, which are valid formulas. Then alpha or beta, alpha and beta, alpha implies beta, not alpha. All of those are actually also valid formulas, right? So notice that what we have here are some base cases, right? The base cases are true and false. And then we have some inductive cases. And the inductive cases are alpha or beta, alpha and beta, alpha implies beta, not alpha. So one of the things that you should see is that this kind of gives a skeleton for an inductive proof, for proof by induction. And the skeleton is, well, if I want to show some property about Boolean formulas, I need to show that the property holds for true and that the property holds for false. Those are the base cases. And then I need to show that if it holds for alpha and it holds for beta, then it must also hold for alpha or beta. And it must also hold for alpha and beta, and so on. And those are the inductive cases, right? So there's the kind of the deep connection. If you have an inductively defined type, a lot of times when you write a program that works on that type, you're actually using recursion, and the recursion is kind of guided by the inductive definition of the data type, right? So how would I do something that worked on Boolean formulas? I would have an if statement that says if the formula is true, then do this. Else, if the formula is false, then do this. Else, if the formula looks like alpha and beta, right, and so on. And those would use induction. Like I'm gonna have to call myself recursively on alpha, call myself recursively on beta, and then combine those, right? Think of how you would write an evaluator that takes a Boolean expression and then decides whether it's true or false, right? So that's how the type guides the recursion, and then in turn that will guide the proof skeleton for using induction, right? So you'll see all these ideas kind of combined into a single whole. Okay. So let's look at one example of an inductively defined type, and that is a list. Okay, and a list looks like this. It's just a bunch of items, one after the other, right? For example, you might call this a linked list in a data structures class, right? That's a pretty often term for it. You might call this a vector, right? Depending on your programming language, right? You might think of it as an array, again, okay? Although I'd rather you didn't, right? Mostly because when we talk about arrays, we think of being able to access any of the elements, like a sub 7, in the same kind of speed as a sub 3. But for lists, you'll see that that actually getting to a sub 3 is faster, because you always have to start at the beginning and then work your way to the end, right? So try not to think of it as an array, but definitely think of it as a linked list, or think of it as a vector. And in fact, in Java, for example, you have data types like array list, right? Which is actually a it's a list, right? It has a first element and a whole bunch, right? Now, here's how we're going to define it inductively. And what we say is that a list is one of two things. It could be the empty list, okay? Or it could be a first element followed by a list. So right here, this, right, is A1 followed by the list A2, A3, and so on up to A sub n, right? So this is the first element, and that is a list. Okay, now let's look at some actually like more programming versions of this, right? So in ACL2, okay, ACL2 or ACL2S, which is, you know, a variant of ACL2 that has a nice GUI, then what you have is an empty list, which is nil, right? This is a constant, nil. You might remember that nil was also true, okay? I'm sorry, take that back. Nil is false, right? And t was true, okay? Yeah, it's the same nil. Sorry about that. But when you see nil in an ACL2 program, it could either be false or the empty list. Depends on context, okay? Now, the other thing that it could be is cons a nil. Cons is a special function. And what this function does is it takes two arguments. The first element can be anything. I mean, the first argument can be anything. The second argument has to be a list. And cons AL is a list that has A in front of the elements of L, right? So in this case, for example, A1, A2 up to A sub n, A would be A1, and L would be the list that has A2, A3 up to A sub n, right? So just as before, this is just the syntax for that idea. It's either an empty list, nil, or is an element A followed by the elements in a list, cons AL. Okay, all right, so that's ACL2, right? Now, that's not the only language that has lists. Here's another notation that's often used. So we'll just use a list by putting the elements in square brackets, just like A1, A2, A3 at the top. And here, the empty list is just open bracket, close bracket, which makes sense, right? It's a list that has nothing in it. And then we use this notation where we have a list consists of A, and that means followed by, okay, is the vertical bar, right? A followed by L, where L is a list, okay? So this is actually the same as A1 followed by A2, A3, up to A sub n, and this has to be a list, so let's put it in the right form, okay? So that's one of the other notations, right? This notation comes from a language called Prolog, and it's been used in many other languages as well. So it's kind of a popular notation for lists. Okay, now let's go back to our basic ideas here. And what we have is that a list is an empty list or a first element followed by a list. And this is an important point. It sounds petty, but it's really important. This definition covers all the cases. So no other object can be a list. So if I give you some object and you look at it and you go, wait, this is not the empty list. Like, for example, I can give you a string like Fred, okay? And you look at Fred and you say, is that the empty list? Why, no, it isn't, okay? So then, is it composed of a first element followed by a list? No, actually, it's just a bunch of letters, right? So it isn't any of those, so that is not a list, okay? So now what we have to kind of look at is, okay, so what are all the lists? And the answer is that all the list is, well, the smallest set of things that contains the empty list, and that is created by applications of this rule.